I wait a little bit, 10 seconds. Okay. Good morning, everyone. Respected conference, dear professors, dear colleagues, dear friends, I would like to welcome everyone on behalf of Hungarian University of Agriculture and Life Sciences and Faculty of Food Science and Technology in the 6th International Biosystem and Food Engineering Conference in Budapest here in the Lourdes House. It's a great honor for us that we can provide the venue for this conference, and we thank you very much for accepting our invitation, and you are here and we are together, and we can talk about the new results, the new idea, and we can talk about the future. Your participation will raise the standards of this conference in this event. Allow me to share about the food sectors and food economy, connection between food science and the factory and practice. The international situation has also pointed out the importance and the strategy role of the agriculture and the agri-food sectors. Cooperation in the international level is essential of the development and of the agri-food economy. Collaboration between the science and the industry, the practice and the scientific results, application and the scientific results in the practice is the most important, play an important role. It's our duty, not only duty, the responsibility at the same time is an opportunity for us to develop the sectors, the agri-food sectors, of course. We must set examples for the younger generation that by the working together, the collaboration with the common results and discussing the results, and we are able to develop the food economy and ecosystems. This is the basis of everything. There is the food, the water, there is the sustainability, the agriculture, the fruit production. That is the future assured. This is a reflected knowledge and the knowledge transfer, as well as research and development and the innovation. Universities and research institutes have a prominent role of the responsibility in this. So let's join force, compete with the common strengths in the international field, international area, in the networking, compare our truths, generate products, just as today's conference is a good example for the cooperation, joint research and development, and the appearance of our students in the international arena. Let's provide student exchange and development opportunities for the young people because they are the future. The 6th International Biosystems and Food Engineering Conference and the Professional Forum of the Institute of Food Science and Technology of Hungarian University of Agriculture and Life Sciences, the BiosysFoodEng Konferencia, which has launched in 2016, has now grown in the international recognized forum where the latest results of the food industry, agriculture technology and engineering are put in the spotlight, in the focus. The 2025 BiosysFoodEng Conference in the 6th occasion, during which the international area for science, the innovation and the professional community meet. The scientific professional forum provides an excellent opportunity to discuss the latest scientific results of certain segments of the agriculture and special areas related to food science and to build the relationship between the countries, between the university, the international partners, as well as to further deepening exciting relationships. The conference focused on the current challenge and food printing, food 3D printing, sustainable technology, a new product development, and innovation utilization of food waste. This even is not just the conference. This is a meeting point where domestic and international researcher, teacher can present their work, the results, establish new collaboration, and participate in the inspiring professional discussion. The hybrid format allows interest parties from anywhere in the world to join. This is the digitalization. We will not forget about the young talent here. The scientific committee will award the best poster, and the audience can vote for the best presentation. This is a real platform for emerging researchers to show themselves to the professionals, and the presentation, the results. Inspiration, networking, knowledge, sharing in all in one place at the BiosysFoodEng 2025 conference in Budapest. More than 30 foreign partners, scientific results, partners who conduct high-quality research in the field of agriculture, food science, we come to Budapest in personal form. The specialist section organized a day before the conference with the partners provide the excellent opportunity for the professional exchange and deepening the relationships. The occasion also provide a great opportunity for not only the researcher of the Hungarian University of Agricultural Life Sciences and our Institute of Food Science and Technology, but also food industry development implemented in cooperation with other Hungarian universities, especially with the Cibus Hungaricus Foundation, to be presented and discussed. And finished, I wish everyone a very productive and useful collaboration, conference, new idea, new thinking, and networking, improve the networking next time, and relationship in between the countries, between the university, between the institution and the continents. Thank you very much and have a nice day, have a nice afternoon today, this conference. And the next time, the first section, I would like to ask Professor Zoltán Kókai to start with the first section. Thank you.
The first section contains 4 presentations, and the first presentation will be delivered by Hermanova Sonia, a versatile journey from plastic prototyping to food printing. I kindly ask the presenter to deliver the speech. Thank you.
In front of the auditorium, yeah? It's working. Thank you very much. Good morning, ladies and gentlemen, valuable colleagues. I am very happy to be invited here. And it's not my first stay here at the conference, it's repeated state. And I would like to present my contribution, a versatile journey from plastic prototyping to food printing. In my opinion, 3D food printing is a combination of culinary art, food technology, engineering, and also material science. A successful 3D food printing requires strong, synergic, interdisciplinary collaboration. That's why I am here, a polymer chemist, material chemist with the experience in 3D plastic printing, together with colleagues from food technology department. Well, I would like to show you the concept of the 3D printing from the plastic prototyping to a meal to food with the composition of special ingredients. Well, about the research topic, the concept of 3D plastic printing was introduced in the 1980s. And the first report on 3D food printing dates back to 2005 or 2006, like 19, 20 years ago. And it's an additive manufacturing. It's a technology which enables you to create 3D geometrical edible objects by layer mode. The first edible ink was chocolate, and seemingly it's a very simple material to work with, but it isn't so easy. It's quite a difficult substrate to work with, and I will show it for you in our results. How we moved from 3D plastic printing to 3D food printing. So I will show you the basic steps which can be utilized both for plastic and food printing, and we can combine the pieces of knowledge to be successful. And last but not least, I would like you to show the idea of introduction of 3D food printing to curriculum of new generation of food technologists and engineers for the future solutions. When I simply add the keywords 3D food printing, the Web of Science database, you can see that there is about 20 years of research and also interest, effort in application outcomes of 3D food printing. The first experiment, there were only single experiments on the chocolate or sugar-based food. And you see that the research effort has continuously increasing, but we can see the major interest in last years, in last decades. From, we can say, more simple experimental work to more complex food. Also, new 3D food printers were developed to work to handle with special food ingredients. Important thing is that we are moving not only to 3D food printing, but to 4D food printing. It means that we introduce temperature-sensitive hydrogels. We can obtain another property which will be shown during the time by the change of temperature, for example. Important thing is that about 80% of published work meets some sustainable development goal, one of the 70s. And the majority of the work is connected with the SDG goal number 3, good health and well-being. Then also number 8, industry innovation and infrastructure. And then sustainable topics like sustainable cities, responsible consumption, life on the land, and climate action. It means that 3D food printing is moving to bring solution in sustainable issues. Especially, it's not about food safety, but food security, responsible transportation, storage, production of novel food, and especially reuse of discarded food waste. So additive manufacturing enables us, these techniques or technologies enables us to prepare complex design, which are difficult to be achieved by conventional method. We spend time and it takes effort to make such complex structure. So we will start in digital space with creating of different shapes, different geometries. And moreover, we can also create novel textures and also the compositions. We can combine different composition of food matrices, and then we can personalize food product just on demand. So it's customization in food design and production. We can already create a gallery of physical objects. And before mass production, we can play with it and we can already evaluate how they are perceived by some group of consumers. So it's a reduction of time and especially food matrices which we need for experimental work. Chocolate, this is only white chocolate because I had at home white chocolate, but you need to know that chocolate, it's quite broad term. It depends also on the country. What does it mean in the Czech Republic? If it's white, dark, or milk. Important is the percentage of cocoa butter, which melts and crystallizes. And this is crucial for chocolate products creation by 3D printing, because we need to very control the temperature to have it in this interval of 32 and 40 degrees because of the most stable crystalline form, which is also very well accepted by the consumers. Why chocolate? Why people start with chocolate and why I selected chocolate? Because I think that consumers are already used to different shapes, different forms of chocolate, some novelty. So they can accept it easily than when it's made from fruit or another type of like whey protein and so on. Chocolate can be a little bit customized. We can make forms with reduced sugar. Then also it can be enriched with whey protein or extract. There are already published work on a mixture chocolate with ibuprofen, paracetamol in pediatric healthcare to prepare something which is attractive for children patient and avoid these pills. So chocolate offer a lot of potential with creating new forms. Studies in the literature are also very promising because people can accept the new chocolate products prepared by 3D printing. They are willing to pay, and also they come second time to eat it, to buy it. Another experience, it's wow experience. It's something that has enhanced value. For example, if in the restaurant you receive a 3D printed chocolate cup with dessert, you eat it and you say, wow, it's something amazing, it's something new, it's delicious, yeah? Instead, if you use just like ceramic holder and so on. So from this point of view, chocolate, it's not bad substrate to start with the 3D printing. And now I would like to highlight the process before 3D printing. These processes are a little bit overlooked by researchers. And in my opinion, this could represent weak point in successful 3D printing. So what are the common substrates which are printed? In addition to chocolate, it's mashed potatoes. They are available, economically available, and you can prepare them repeatedly to have the same consistency and to print the different shapes. Then the big issue is meat and meat substitutes, because we need to have realistic fiber alignment like a steak. And when the meat is grown in the laboratory, there is missing fat component. And to have this taste like a meat, real meat, you need to mimic to have a realistic texture. More challenging is plant-based, because we spent a lot of time with preparing hamburgers, mini hamburgers from soy-based protein, and it's pretty difficult to mimic the realistic texture. Then desserts, I think that desserts have this economic potential to be presented, to be introduced to fine dining and restaurants. And however, staple foods, it means like from dough, pasta and pizza. But we know that after using by these three mixtures, we need after 3D printing have additional heat treatment to cook, to bake, to be edible. So let's look for these 3 steps, and these 3 steps I use in our laboratory and in our research. First step is model design. We use Tinkercad, which is freeware software, and we can model different shapes. However, I oversimplified it for plastic, but a piece of cake, it can be done also in plastic form. And we use the same program for modeling the prototypes for both plastic. You can see plastic 3D printer classical. It's not from chocolate, it's plastic. And this is the 3D food printer. And the second step, you need to slice your object. And this slicing is already specific to 3D printing. You need to have your own software, because at this step, it's not only slicing to individual layers, but it also you set the type of material, the processing temperature, the extrusion rate, and all the parameters are supposed to be done in this step. Then is 3D printing, again in your 3D food printer or 3D plastic printer. And for plastic, it's already done. But for edible objects, sometimes we need, not for chocolate, but for cake, for dough, we need to have this additional thermal treatment, which is even challenging because you need to have the same form and shape, the same geometry after this process. This is another very challenging step. So for 3D printing, because I am most interested in biodegradable polymers, I stayed with PLA, like biodegradable, and unfortunately only one filament on the market is attested, is certificate to be in touch with food. Yeah, so and it's quite expensive, but it doesn't matter because nevertheless, it saves a lot of time and energy. So printing parameters, you have got your 3D food printer and you would like just to add your food to the cartridge and you would like to push the button and the print. And this is the tricky point because you need to adjust the printing parameter previously. And it seems easy that you will read a couple of papers and you will just copy the printing parameters and it's done. Unfortunately, it's not working in this way. It's empiric work that you need to set infill pattern. It means like mesh or honeycomb-like percentage, because usually you don't want to have 100% infill because it's, for example, chocolate, it's quite expensive material. Then processing condition, you have got different nozzle diameter, printing speed, extrusion rate, and also layer height. Usual layer height, it's like 1.5 millimeters. I think it's the standard one that you have got nice fine structure and it doesn't take so much time. And important is temperature control. Generally, there is a triangle rule that these three parameters are supposed to be in balance. Yeah. Otherwise, as you can see, I don't know if it's visible, the face, yeah, the rheology, because we were asked to print a face of Johann Gregor Mendel, the father of genetics. And you can see that it wasn't possible and we received like a lion face. So it can be also the results with wrong conditions. Here you can see the example of different printing speed. So the food is the same. We have got the same parameters. What we played with the printing speed. If it's too quick, you lose your geometry. So you need to prove to receive some optimal values before time spent and the geometry. And what we did to prove our proof of concept. So I started, that was my experience with 3D printing, that was my line. I start with the modeling, like simple shape, like heart, ring shape, star shape. And we model it for plastic weight. We start with the same models, with the same dimensions, the same parameters. And we continued by plastic way. And then also we continued with chocolate. And then we compare the results. You can see printed ring-shaped objects. And here you can see 10 layers. So this is the layer structure. So it takes 1 minute and about 20 seconds. And we can see according to parameters, weight, height, and width, its outer width, that it was quite the same, the results, and it's reproducible. With new product, we usually prepare at least 20 samples to be assessed to assay the printability. Yeah, so 6 samples is only to proof, but this is no chocolate, but 20 samples at least if you play with new one. Star, you can see that also 10 layers, but the time is 1 minute and 25. And we can also see that the height is 5 millimeters and the width was 20 millimeters. So we can see again that we have a sample to be assessed about the reproducibility. And the last one was heart shape. So we did it that we had 3 shapes for plastic and 3 shapes from food. And here you can see the comparison of the result. We compare not only the geometry accuracy, but also it's called printability. So what do you expect it? What do you program and what do you receive? And this is very important. So we can see about the height, it was 5 millimeters, 10 layers. So it should be self-supporting, the layer, not collapsing the structure. So we are almost at the level of 5 millimeters, so very good printability. The width, it means outer dimension. And again, we are very close to 20 millimeters, like in plastic case. Wall thickness, this is very problematic to have like this 2 millimeters wall thickness, because 2 millimeters is the least diameter for PLA plastic printing. So that's why we kept the same, but we were more or less within the range 1 millimeter plus and minus. The white is indicator of homogeneous sample. Yeah, if there are bubbles or solid substances, because you know the chocolate is like a suspension of solid particles in cocoa butter phase, and you need that the chocolate flows under the temperature of extrusion, but it solidifies when it's deposited on the build plate. And then I would like just to say my vision about introduction the 3D food printing to classroom. I took the samples, I took the 3D printer, and I implemented it into my lessons in food processing. And the students were shocked because there is a negative perception or insecurity perception that 3D printed means something which is like full of additives, stabilizers, yeah, that is not healthy. And it was difficult to explain that the all processing is the same before 3D printing. The ingredients like cocoa beans and other components were mixed, blended together, then conched, tempered, and molded. So these steps were the same. The 3D printing was only the last step to prepare new form in addition to conventional form. And I think that when we convince young generation of food technologists and engineers that 3D food printing can be a way, 1 minute, I think that we can have a communication channel to wide range of stakeholders and to solve issues like in new perspectives, sustainability and food security. This could be a communication channel. And last one is that I'm now interested on the project preparing new edible gels for patients suffering with dysphagia. And especially we use mashed potatoes, not chocolate, unfortunately, but it doesn't matter. And also cooked vegetable. Thank you for your attention.
Thank you very much for your very interesting presentation. I think it was a good startup to see that food science is always develops and brave enough to go on unexplored ways. Due to the strict time frame now, we don't have a question and answer, but in the break, I encourage everyone to call our presenter and discuss the details. Thank you very much. Our next speaker is Damir Magdic, Climate Change Patterns and Their Influence on Wheat Quality in Eastern Croatia. I kindly ask you to deliver your speech.
F5 doesn't work. Okay. Oh, geez. Thank you. Good morning, ladies and gentlemen. My name is Damir Maglic. I'm tenor professor from Faculty of Food Technology in Osijek in Croatia. I will talk about climate change and wheat quality. It's an important theme today. My country is here, and we work together with. Sorry, I don't have each display here and here. We work in eastern part of Croatia, in heart of Europe, somewhere under Hungary. We are 3 kilometers from Budapest. Climate change impact on wheat quality, on wheat yield, and impact on food industry. It's a very big problem for food industry because global temperatures increased, heat waves, and we have low quality of wheat, and we need to add additional work and additives in food products, so it's very cost. It increases costs. Shifting rainfall patterns are also problems because we cannot predict what will happen next year in harvest. So it's a very big problem. Some of major factors for wheat growth are temperature, water availability, and soil quality. So temperature reducing wheat yield, declining nutritional quality, shortening grain filling periods, decreasing mineral content like zinc and iron, and altering gluten properties, which are important for bread from dough and for bread making quality. Every year we have changes in rainfall patterns. Droughts reduce yield, warmer climates leads to increased pest infestations, we have fungal diseases, and inconsistent water availability lowers wheat kernel weight. Also, we have soil degradations caused by rain years, soil losing nutrients over time. Increased concentrations of carbon dioxide accelerate photosynthesis and boosting wheat growth. For some plants, it's over 50% faster growth. So it's quite a big problem. It lowers grain protein content and reducing nutritional value of wheat. Of course, we have possible solutions, and we do some actions on that field. New cultivation techniques, for instance, crop management practices, crop rotation, farmers adopting drought-resistant wheat varieties. We can use breeding and genetic modifications, and we do, to prepare early maturing varieties, enhance photosynthesis, and exploring alternative grains as substitutes. And that is one of most important tasks today. Of course, we need to do something about public awareness and educate people. We need to encourage public to involve in sustainable food systems. We in Croatia have once per year wheat field days, and we do review of wheat cultivars and practices. We do that with corn, with barley, with other cultures. So we try to educate farmers how to produce better yield, better wheat. Future projections for wheat productions are very bad. Estimation shows that 5 to 10% yield decrease in coming decades will be. This is because of climate change, high risk in productions, lower profit in wheat production. So we need to call people to action. Firstly, we need to educate or to elect educated politicians to recognize this as a big problem. We need to keep supporting sustainable farming initiatives. We need to advocate for policies that addressing climate change, we need to educate farmers, food producers, we need to share knowledge. So let's share knowledge. I will show you influence of climate change on wheat quality in Eastern Croatia. For the last few decades, I analyze bakery products from wheat cultivars from Agricultural Institute in Osijek, and these are results for 15 years in consecutive row. So I used 24 wheat cultivars with 21 properties in analysis. Wheat cultivars created at Agricultural Institute in Osijek, and Divana is Croatian wheat cultivar of the highest quality, and Divana is used as improver in all our products in Croatia. My part of job is bakery products analysis, descriptive statistics, chemometrics, image analysis of bread slices, and similar things. So I asked from Croatian Meteorological and Hydrological Service in Croatia that collected meteorological data for last 20 years. So they sent me the data, and we have cumulative precipitations for 2 periods and temperatures of air. We choose periods from October to July. It's vegetation season for wheat. And also we choose period May and June. It's harvested time and filling grain time. And of course we have temperatures of air. And these are mean values for 15 years. So you can see this. What's the problem? We have more rainy days in period before harvest. So you can see it's almost 35% of variations from year to year. It's huge, huge problem in agriculture in Croatia. And you see whole vegetation seasons have huge variations. Temperatures variates lower. And when I tried to define trend of those climate change in Croatia, I found this. Linear regression showed that every year we have positive trend in cumulative precipitation rises. It's about 0.1 or almost 1% per year or more rain. And when I analyzed temperatures, I also saw that temperature rises from year to year. So we will have problem in next years, in next decades. Coefficients of determinations are very low, so it means it's really unpredictable. When I tried to use 6-degree polynomial regression, I obtained the same results. I saw it's inconsistent. I cannot predict anything when weather is in question. So we have unexpected patterns in climate change, and it was till now, and it will be in future. So we need a global strategies to ensure food quality and food security. Every year, for the last few decades, we analyze over 20 parameters of wheat and wheat flour. So we analyze 3 agronomic properties: yield, hectoliter mass, 1000 kernel blades, 6 indirect quality parameters of wheat flour, farinographic properties, extensographic properties. Those properties are the most important properties for food industry. So when we did analysis and when I collect those data and make some statistics, I calculated this variability of those properties for 15 years. You can see that breeding activities made success in last 15 and 20 years. We have almost 9% variations in protein content in wheat. It's fantastic. It's very big success for breeding division. And it's quite good. We can work with it in food industry. But yield varied from year to year almost 20%. And you see, when you have 6 tons of wheat per hectare, perhaps next year you will have 5 or 7, and 5 is not enough to be successful. You cannot live with 5 tons per hectares. You need to have 6 or more. So it's a problem. Some other properties important for food industry are also very variable, and you see they're about 20%. But the most important, wheat flour properties important for food industry are varied over 20% and almost 50% stability. So we cannot produce every day the same food product. We need to put additional work in the job. We need to put additives, and it means increasing costs of production. So it's a huge problem on planet. Of course, I try to do some correlations among climate change and wheat quality. So when I analyze temperature impact, you see temperatures in May and June. It's in filling rain time and before harvest. High temperatures have strong, significant negative impact on sedimentation, wet gluten, and water absorption in wheat dough. When we analyze cumulative precipitation, rain, it's also negative, significant negative impact on yield, on hectoliter mass, and 1,000 kernels weight. So we see that climate change have strong, significant negative impact from year to year on wheat quality and food industry. So it was the same for all time. And after that, I tried to do something new, something never seen before in literature. So I try to connect above average years for each property and above average years in climate. And it's something fantastic. You can see the blue cells are rainy years. And you can see for last 15 years and for last 20 years, we always have the same situation in May and June and whole vegetation season. Whenever we have more rain before harvest, it was rainy year for whole vegetation season. So you can see that. Sometimes we have normal year with no above average values in climate, but sometimes we have very hot and very dry year. It's also not good. So I try to connect those phenomena with indirect quality parameters of wheat, with farinographic and externographic properties, and with yield. So you can see when we have a lot of rain through the vegetation season, we have bigger yield. It's okay. But sometimes we have big yield in very hot and very dry years. So we don't know what happens. It's biology. Sometimes we have normal year with big yield, and we have normal year with normal yield. So we cannot find a pattern. And when I try to connect low variations with all those things and with climate, I found something interesting. When we have hot temperatures in May and June, we have lower variations in wheat properties. Whenever we have hot May and June, we have stable production, industry can relax. But whenever we have different situations, all these properties changed. Those are rainy years with above average values. Dots are for above average values. And those are hot and rainy periods, hot and rainy years. So you can see some patterns in climate change. And this one is most important from this analysis. Now we can see that every 2 or 3 years, we will have more rain. So we can do some actions about that. Sometimes, even if we have a very hot and dry May and June, we have also a lot of rain. And in that year, it was 2018, we have the smallest variation in wheat quality. Big temperature, big rain. So it's something that not expected. The same situation was for last 5 years. And this is breeding success. You can see, whatever year was, we always have normal or above average protein content in wheat. This is caused by good breeding process at Agricultural Institute. We have stable yields, we have higher protein contents, and it's quite good. The same trend is for last 5 years. So we definitely know how to produce high quality wheat for different climate. But we are facing a new problem today. That is this. But let's look the numbers. Before 2025 years, human populations was 50 million people on planet. After 1 millennium, it was 400 million people on planet. In next 900 years, it was 1.6 billion people. And in only 100 years, it increases on 6.2 billion people. This is the biggest task for food industry. We need to ensure food security and enough quantity, enough amounts of food. In last 25 years, we have 2 billion people more on planet. Estimations are that in next 25 years, we have 9.8 billion people on Earth. And at the end of this century, we'll have more than 11 billion people on Earth. So from this, in 100 years, we will have almost double number of people. Do you know what it means for food industry? Pardon me. So we cannot do only usual practices. Is it genetic modification good for us? Breeding wheat strains resistant to heat and drought. Sequencing and Sequencing and editing genome of crops can lead to healthier, more nutritionally resilient plants. Biohacked wheat, yes or no? Do we have time to wait? In 1999, in Cartagena, in Colombia, 170 nations signed the Cartagena Protocol on biosafety. In that moment, it was biosafe or biosorry because of patents, monopoles, dead seed, risk for human health. Firstly, 126 scientists signed it from 24 countries. And as you can see, where the trouble, there I am. We just try to say, slow down, we need to control the consequences. And one of the results was producers must clearly label GMO content on food. Do we need genetic modifications today? Perhaps we'll find answer today, perhaps not. But is this what we can expect? Or is this what we want? It's for you. It's for you to answer. Thank you.
Our next speaker will be első Angelina Cavella, the impact of drying technologies on the polyphenols and antioxidant capacity in chokeberry pomace tea infusion. Please deliver your speech in 20 minutes.
Good morning. Good morning, everyone. So I'm első Cavella, and I'm going to present to you the impact of drying technologies on the polyphenols and antioxidant capacity in the chokeberry pomace tea infusion. So actually, this is the chokeberry, and this is actually the pomace. Basically, okay, yeah, it's working. So basically, the pomace is a byproduct of juice processing from the chokeberries, which are also known as aronia, coming from the Aronia melanocarpa, which is a shrub originated from eastern Canada and eastern part of America, but it has now spread across Europe. It's also grown in Hungary, and that is where we get our samples from. So, but then when it comes to this fruit, it is hardly consumed because it has a bitter taste. However, it is produced in, it is actually produced, or it is processed into other products, such as the juice, and also this appender. This is readily available in our markets. You'll find it in Lidl, Aldi, or I think in all the shops around. So now during the production of these products, there's a large amount of pomace that is produced. And the pomace is often actually processed into animal feed or just discarded into the environment. And actually, if we discard it into the environment, then we have a problem. We're already complaining about the climate change. And when you dispose it into the environment, there's a lot of gases produced. And that is what we actually blaming. That is what we are complaining about, the climate change. So, and the aronia pomace itself, and that is actually our interest, is the polyphenols. It is a very good source of polyphenols, which have functional properties, such as the antioxidant effects, antimicrobial effects, and also health benefits. That's why in this case, we are utilizing it as a tea ingredient. And we also have other potential. It can also be used in the food industry, such as antimicrobial can be used in the food industry as an antimicrobial agent, color enhancer, because it has a very good color. And it can also be used to extend the shelf life of other fruits or even meat because of the antioxidants. And for us today, I'm presenting to you actually this aronia pomace as a tea ingredient. But then for us, again, to be able to use it as a tea ingredient, we have to process it in a way that it is actually easy to handle, and it should be actually a quality pomace. And Mostly this now processing, it involves the dehydration of the polymers. That's the only way you will be able to handle it with ease, and also to be able to store it. And we have now different technologies that are used for drying the polymers, or to say for drying the fruits in general. However, we do not know the best drying technology, or to say the optimal technology, the one that is going to give us the polyphenols that we are interested in the polymers, because that is our main interest. So therefore, our study, we actually aimed to produce, or to say to dry the polymers using different technology. We chose actually 3 from all the drying technologies that are used to dry fruits, because we are looking at the technology that is going to preserve, or that is going to retain the maximum polyphenols in the product, in the polymers, and also that is going to give us that rich color that is in the aronia polymers. So, and after that, we then had to use it because we are looking at the utilization of the aronia polymers. We don't want to throw it in the environment, and also always using it in animal feeds. We are wasting the polyphenols. So we then had to make, after drying, we made the tea, the aronia polymers tea from these polymers. So so the dry technologies we have chosen, it was the freeze drying, the microwave drying, which we have divided into 2, with 1 minute of microwave radiation and 1 minute actually passive period, and the whole process took 60 minutes. And also the second one is the microwave with 1 minute radiation and 2 minutes passive time. The whole process took 90 minutes. And the third one is the atmospheric drying. And we chose these technologies based on the energy efficiency and also the time to process. And not only that, but these are some of the the technologies that are cited as best technologies to dry fruits. And then after drying, we then had to infuse our polymers, and we used the total sample. It was 3.5, and we used 100% aronia samples, but then we also had to add, because we are saying that it doesn't have that good flavor, we had to use a market tea to just enrich it with a flavor. And this is actually the composition that we have used. That's all we have, 100% aronia, and then we have 50% and 60% aronia. The rest we substituted with the market tea. So, and this is the market tea that we have used. You can see the composition here. This is the composition of the market tea that we have used, or to say the ingredients in the market tea that we have used. The tea, we prepared it by infusing, because we say the total sample was 3.5 grams, and we added the 200 ml boiled water to it, and then we waited for 5-minute diffusion, and then these are actually our samples. These are the outcomes to say. This is the 100%. We can see that the color, and this is the market tea that we have. You can see the difference in color. And this is the microwave vacuum drying, the 1 minute, and this is the microwave 1 minute, 2 minute. And this is the freeze drying samples, and this is the atmospheric drying samples. So after that, we then had to test for polyphenols, because you remember our aim was to test the effects of the drying, the drying technologies. So we had to test for polyphenols, and we also had to test for the color, because we are also interested in the color. Because for all of us, when you go in the market, we always look at the color of the product. We always want that product with a very good color. And we analyzed our samples with the IBM SPSS statistics, and then that now brings us to our findings. So these are finding when it comes to color, and that is something you have also seen in the pictures, that there is a difference actually between the 100% symbols and then the other percentages when we reduce the aronia and then we substitute it with the marker T. And of course, the reason is because we wanted to enhance the flavor of aronia since it doesn't have any good flavor. But then with the color, we wanted to see now if we add other product, if we are to substitute certain percentages of aronia with other with the marker T, then how is the color going to be? So we looked at the color change between the 100% aronia and then the one that is substituted with the marker T. So, and you can see that our result actually ranged between noticeable and great visibility. So meaning that the more you substitute the other product, but that, I mean, that is obvious because the marker T is lighter compared to the aronia symbol. Obviously, if you remove more and add more of the marker T, the color is going to change anyways, and the differences are actually visible. We can actually see here. This is the market. This is the 100%, and you can see the 50%, and you can see the 60% here, and that applies to all the symbols. And for the total for the polyphenols, we looked at the total phenolic content. We looked at the andocyanin and the antioxidant capacities using DPPH, TEAC, and FREP. So for TPC, which is total phenolic content, we actually, you can see with this graph that the 100%, of course, it has it's obvious it will have high polyphenols compared to the substituted symbols. But then now, this is where now we look at the differences between the drying technologies. But if you look at this, of course, we can see that the freeze drying is the highest. However, it was not significantly different from the other three technologies. And for this is the marker T here. So you can see that it has really low total phenolic content. Basically, that is because of the ingredients in the marker T. We have the blueberries that are also good, but then, you know, there are other also ingredients. So, and for total andocyanin, which is responsible for the color, we see that the microwave drying is actually the highest. It gave us the highest because this is the microwave drying 1 minute, and this is the microwave drying 1 2 minutes, and this is the atmospheric drying. In this case, we even had the freeze drying with low, which is significantly lower than the other three technology, but it was actually the highest here. But for andocyanin, but I saw that also in the color. The andocyanin is the one that's responsible for the color, and it actually it conforms with the results of the color. And for the antioxidant capacity, this is actually something that I had to overlook. Somehow I even had to repeat the experiment because I didn't want to agree with this, because I expected the result to be somehow the same as the total phenolic content, and also for the antioxidant, the total andocyanin. However, this is just what it is. So we can see that, okay, with the FREP, we have again the microwave drying and the atmospheric drying with the highest total andocyanin compared to the freeze drying, which is not a case. And with the DPPH, we can see that there is no significant difference between all the samples, even the substituted one, and that applies as well to the TEAC. And in this case, we even have, with TEAC, we even have the marker T with which is also not significantly different from the other symbol, from the aronia symbols. So so now looking at our results, so we can only summarize that our samples, we found that the freeze drying, or to say, all three technologies that we have used are actually good for drying the pumice. We saw that the freeze drying, it gave us the highest. However, it was not significantly different. That tells us that we can use any of those three technologies that we have used. However, it depends now. That is going to depend on the energy efficiency and also to say on the resources. If you can use the microwave, if that is what is available to you, it's also good enough. If it's freeze drying and that is available to you, that is also good enough. So we have so many articles that are citing freeze drying as the best drying technologies, but I agree somehow when it comes to fruits, because we don't have articles on the pumice, but we do have on the fruits. Because with the fruits, when it comes to freeze drying, it actually preserves the color. If we go back to my, okay, let me use this. If you go back to the pumice, sorry, just want to go to the pumice. If you go back to, okay, this is not, but on the computer is better anyways. So if you go back, this is the freeze drying, but just that it's not quite clear. But these are too dark. If this were fruits, these were too dark, and this actually had a good color to say, and this is for the freeze drying, and that is why I understand why the articles are citing freeze drying as the best drying technologies. But not only that, we also have our study results conforms with articles as well, because they also cited microwave drying as a good technology, microwave vacuum drying as a good technology to preserve polyphenols and also antioxidant activities. And we can also conclude that we can use the pumice as a tea infusion, or we can say we can use the pumice as a tea ingredient. If we don't want to use it as probably because of the flavor, we can then add to other tea. We can actually improve other tea quality in terms of the polyphenols, because we all want antioxidant, we all want foods that are rich, that are actually going to even that are going to reverse those effects in our body. Those, if how do I say it? I don't want to say diseases, but you know, those that are causing cancer, because the polyphenols are actually going to reverse those effects. So, and we can also enrich other products with this good color that we find in the pumice, and that is how we can actually use the pumice in the food industry. Just want to acknowledge actually the Stipendium Scholarship for supporting my study, and also Instavan Del Nadi for helping me with lyophilization, and Richard for providing us with the aronia fruits, and my lovely supervisors there. And yeah, this actually, thank you very much for listening. And just in case you want to know more, to hear more about our aronia pumice and its uses, or to say the possible utilization of aronia pumice, but I only have 15 minutes, unfortunately.
Now it works. Thank you. Due to the very good time management, we've got 2 full minutes for questions and answers now. So if someone has a question, I can give you the microphone.
Hello, thanks for the presentation. My question is, have you applied this to food already, and have you tried that in the technology, your coloring?
What do you mean if I have applied it to food?
Yeah, if you have tested it in a food. No.
No, actually, I don't know what you mean to food because,
Okay.
you know, this tea infusion is also food. Anyways, actually, we did not add to say if it's about the color, we did not add because this another, I have my junior doing the same. So she's the one going to add the color to the food to say.
Okay, yeah, that was
But I'm looking at the other possibilities, like you can see this is for antimicrobial activities. So it can actually reduce or it can inhibit the growth of Listeria, which is actually the most feared microorganism in the food industry, and also Staphylococcus. It can inhibit Staphylococcus, and or to say most of the gram-positive bacteria, it can inhibit the growth, and yeah, and the tea, we can make the tea from it. That is food. We can drink it.
Yeah.
And for me, even if you're saying it doesn't have a good taste, actually I test it myself, and I'm not. The taste, it doesn't have a problem actually. Just that probably if you like flavors, we'll say it doesn't have any flavor, or to say that of course the flavor you're looking for, but then it is good. It's just similar to if you have tasted the 100% hibiscus tea, it is the same.
Okay.
So we can actually use it. And we looking at the regulations, there are no restrictions that you cannot use the pomace. So we can basically use the pomace as a tea infusion.
Okay, thank you.
Thank you very much, and also for your talk. And now, thank you for your speech. It was an interesting topic. And in the first section, we have one more speaker, Pramod Mahajan, Sensors, Modeling, and Digital Twin Applied to Fruit Packaging and Storage. Kindly ask you to deliver your speech.
Hello, good morning, everyone. My name is Pramod. I'm from Germany, Potsdam specifically, Leibniz Institute for Agricultural Engineering and Research. Today, I'm going to talk about the sensors and modeling and digital twin for packaging and storage of fruits and vegetables. Most of my talk will cover Apple as a case study. So because in Germany or most of the Europe, we store apples for nearly 12 months. And yeah, so I will talk mostly about the Apple storage, the cooling, control atmosphere, and all those things. Yeah, so Apple is still alive after harvest. It means it respires, it breathes, it consumes oxygen, produces carbon dioxide. Okay, and it goes slowly through many different processes, like it produces the heat, it loses the weight, and it degrades the texture, and it shrinks. So many things happen. So it is a live product. So it's a big challenge to pack or to store such a live fruit. Over the past 2 decades, we have made a very good progress actually for packaging and storage of fruits and vegetables. If you're talking about packaging, we started with modified atmosphere packaging long back, at 20 years back. It's just a simple modified atmosphere packaging to create oxygen and carbon dioxide in the package. Then over the years, we have developed the laser technology to make the perforations in those packages. And then now we have gas control and also the moisture control in those packages. Talking about the storage, we started with the control atmosphere, the basic one, how to control O2 and CO2 in a big storage. Then we advanced to ULO, like it's a very, very low oxygen concentration. And then we advance now to DCA. DCA is a dynamic control atmosphere. It means like we monitor the respiration rate of the apple, and accordingly we control the oxygen. So all these things are happening dynamically. So as you can see, like there is a huge amount of progress we made in the past couple of decades. And what is the reason for this progress? The answer is like the growing precision. Like we have so many things to monitor, like temperature, gas composition, air velocity. So many things are possible to make and assess the cold storage. And also we receive so much data actually from those storages. So based on that, we are able to transform. And now today I'm going to talk about the sensors and modeling. So the sensors are something different than what exist. We already know the temperature sensor, humidity sensor, but what I'm going to talk about is completely different. Okay, so this is the first sensor which I have developed in my institute. We call it gas sensor. So it measures the oxygen and carbon dioxide. Okay, and the size is exactly same as the apple. And this sensor you can place it in the storage. It has no cables, nothing. It's a standalone device. It means it has the microcontroller, the battery, the communication, and all the sensors, including temperature and humidity. Everything is inbuilt in the sensor, and it transmits the data wirelessly to the computer. So this is really nice because we can use this artificial apple in the storage and communicate how it is performing. What we use this gas sensor is to monitor the respiration rate, because the apples, they respire, and at what rate their respiration happens, that we want to know. So we have developed a system. You can see in the picture there, it's a glass jar. Inside the glass jar there are apples, and one sensor is placed on the top. It is a closed system, and there is a pump and all those things. So this entire setup is placed in the CA storage, and it monitors how oxygen is consumed and how carbon dioxide is produced. Based on that, we calculate the respiration rate and also the respiration quotient. So you can see the data here. The top graph shows how the oxygen is decreasing and how carbon dioxide is increasing. So you can see those fluctuations happening in along the time axis. So that indicates that it is respiring, and we use that data to calculate the respiration rate. And you can see at the bottom of the bottom graph. So it shows you the respiration rate in real time, and also the RQ. So based on these parameters, we can control the atmosphere gases. The second sensor is the airflow. Well, the airflow is quite easy to measure, right? You just have the anemometer. You can measure it very easily in the open air in the surrounding. But it's very difficult to measure airflow in the bulk of the apples. Okay, because apples are normally stored in a large bin. There are 300 kilograms of apples in a big bin, and I want to know the airflow in the middle of the bin. How do I measure that? So that was a big challenge for us, and that's the reason we have developed this airflow sensor. So it is based on the calorimetric principle. There is a small silicon diode, and you can see the sensor there. There are 4 plastic spheres, and in between the spheres there is a diode. So it measures the heat flow as a function of air velocity. So we have calibrated, and it works perfectly fine. And we use this. You can also see the sensor actually placed in the bulk of the apples. You can see in the middle there. So we use that to measure the airflow. Okay, and then the application, like we use this airflow. We place this airflow sensor in the different positions of the bin. You can see those in the picture. Like there are 9 sensors placed different locations in the bin, the top layer and the bottom layer, and we analyze what is the effect of external velocity on the internal airflow inside the bin. And we're able to monitor what's happening inside the bin. And with this data, it's it's like we're now able to optimize the design of the actual bin. How many perforations are required? What should be the air velocity? Because we don't want to have too much air velocity, because too much air velocity is actually the wastage. You know, the energy consumption is too high. And so that's the reason we have developed these things. The next one is the condensation sensor. So condensation, I hope everybody knows, when you store the apple in the refrigerator, when you take it out, you see the moisture on the surface of the apple. That is what we call it condensation. Okay. And why it happens? It happens because of the high humidity and temperature fluctuations. Okay. Condensation, we think that condensation is bad because it creates a perfect ground for the microbial growth, because there is moisture on the surface of the apple. So it's perfect place for the growth of the microorganisms and the decay. On the other hand, it's also reduces the mass loss because there is a layer of moisture on the surface. It reduces the transpiration loss. So there are good thing and bad thing about condensation. But how to measure this condensation? There is no sensor exist in the market at the moment to measure the condensation. So we thought about this and developed an idea about this sensor. So the sensor, which you can see here. Okay, so this apple with the two eyes. Okay, and at the bottom you see this titanium film. Okay, it's a electrical conductive film. Okay, it's placed parallelly. Okay, when there is moisture on the surface, it connects the two electrical conductive places and it completes the circuit. And it detects that there is moisture on the surface. So it's a very simple method, but we have developed this in the lab and we are able to use this. And actually this is a self-adhesive film. We just simply stick it on the apple surface, and then it measures. We have some electronic thing to monitor the data and everything. But as you can see, the apple and the sticky film, I think you cannot put it for long. I mean, it's okay for a couple of weeks or 1 or 2 months, but we normally store apples for 12 months. So we need something robust so that apples can last longer. And I was thinking about 3D printing presentation, and it will be really nice to have some artificial apple, and we put this condensation sensor on the apple, and so the artificial apple could properties very similar to the real apple, the thermal properties, I mean, because the moisture content of the apple is more than 95%. So yeah, there is possibility for doing something really innovative here. And not only the wet this condensation, we can also integrate the temperature, humidity, this gas sensor and airflow, everything together. Everything artificial, but actually very close to the real apple, so that we can keep it for a longer period. Okay, so now back to the condensation measurement. I show this graph here, how to make the condensation measurement. We use the thermal imaging camera to detect the moisture on the surface, and it detects very easily, but we compare those results with our wetness sensor, and you can clearly see that when there is condensation on the surface, the signal from the sensor is very low, and when the surface moisture dries, the signal comes back to the normal. Okay, now coming to the modeling, like we have yeah. Okay, let me talk about the sensor first. So in the apple storage, we measure temperature, humidity, airflow, oxygen, carbon dioxide, condensation, and all those parameters we measure. But what do we do with those parameters? There is so much data we generate. What do we do with that data? And my idea is to develop a kind of machine learning or mathematical modeling to make something out of it, because there is so much data we generate. So the model which I have developed is to predict something, like, for example, the shelf life, the weight loss of the apple in the CA storage, how much condensation is there, how much microbial decay is there. So all those things are developed into this mathematical model. Okay, so what I have here is the sensor and the model. Two things are combined together. So basically what happens, the sensor data is fed into the mathematical model, and the model predicts the quality. And based on that quality, we make the decisions. Okay, and all those things happen in real time. I show you one measurement. Actually, these measurements are in the lab. So just 30 kilogram of apples, and you can see on the left-hand side graph showing temperature, humidity, airflow, all those things are measured continuously, and that data is fed to the mathematical model to predict the amount of condensation, the weight loss, the decay, and all those things, which you see on the right-hand side. So this is all those things are happening in real time. Okay, but now this is all happening in the lab. Okay, how about moving it to the real CA storage? Okay, so real CA storage looks different. Okay, there are like 50 tons of apples stored in a single place. So what we did is we installed all our sensors in that apple storage, and we have also developed this a platform, we call it Fruity Twin. Okay, so here what we are trying to do is develop the digital twin. So what is the digital twin? So it's a digital replica of the physical object. Okay, so it means we have a real Apple CA storage, but what I'm replicating is the digital CA storage in the computer, which will show me what is happening in the storage. Now for that we did a lot of work, connecting all the sensors, sending all the data to the cloud, and feeding all the data to the mathematical models, and streaming all the data in real time in the computer. So you can see at the bottom picture, it's actually the television screen where you see what's happening in the CA storage. Yeah, so this is happening in real time, and the distance between this Apple CA storage and my institute is 600 kilometers distance. So it's really happening in real time, remotely. So why does it matter? Because I think this is important, so that it enables the prediction of different things, and the storage operators can make the decisions what to do, when to sell the apples, or how to reduce the energy consumption, and so many things. And this specific test we have done in the south of Germany in the last season, and we are going to replicate again this year, this apple season in September, October. Yeah. So coming to the concluding thoughts, I would like to say the first thing is the established science and evolving prediction. It means we already know the science, what is the effect of temperature, humidity, gas composition on the quality. But what is evolving is the precision. Use the technology to make it better. And now shift toward the data-driven decisions. Now at the moment, like the storage operators, they take the decisions based on their own experience, or even trial and error approaches. But now it's the time to take the decisions based on the data, because we have so much data being collected. So use that data properly to make the decisions. The third aspect is the monitoring the invisible and predicting the future. It means at the moment now we are able to monitor the invisible things like the respiration rate, the condensation, the airflow. All those things are now possible to make the measurements, and based on that measurements, it is also possible to predict what's going to happen in the future. So that is another thing. And of course, the last thing I would like to say is the interdisciplinary collaboration is the key, because one person cannot do everything, because like you really need collaboration from different disciplines like the engineers, the material scientists, the food technologists, and electronic engineers. So everybody coming together and try to solve the real problems. Yeah. So this is my team who is working in my lab. And thank you very much for your attention.
Thank you very much for your presentation on your research field. And now we have 1 minute left because an engineer is keeping the time. So if somebody needs, have a short question, we can discuss now. Yes.
I'm Damir Manglic, as you remember. I obtained my PhD on storage of apples. So I would like to ask, why you choose 5-hour step for measuring? Is it for precision on graph, or it's something other?
Yeah, it's something else, because we don't want CO2 to increase too much. If we measure it for 10 hours, the CO2 will increase to 2-3%, and that increase will affect the respiration rate.
Yes.
So
24 is not divided by 5, so I asked.
Yeah.
What's the reason? Thank you.
Thank you very much. And now comes probably, thank you very much for your talk.
Okay, thank you.
And now comes the section which is the most popular in all conference events, is the coffee break. So we have like approximately 25-30 minutes of coffee break. Please take the time for networking, talking to the presenters, and don't forget at the end of the conference to vote for the best presentation with a QR code. Thank you very much.
So welcome to our next session. We will have 5 presentations, and I would like to ask Bernard Maringol for the next presentation to come to the floor. We will have a presentation about temperature-based classification of pork meat during storage using thermal imaging and machine learning.
Hi and good morning. And my name is Bernard Maringgal, and I'm from Malaysia. I fly more than 10 hours to come here. Yeah. And today I would like to talk about non-invasive classification of pork meat quality using the infrared thermal imaging and machine learning. Previously, we heard about machine learning, real times, and so on with Dr. Pramod Mahajan from the ATB. So now we are focusing on the thermal imaging and machine learning, but we test it on meat. Okay, and I'm from the UNIMAS, University Malaysia Sarawak, and I'm in the middle of Borneo. Okay, another part of Malaysia. And I also representative UNIMAS Agro Research Center and the Faculty of Resource Science and Technology. All right, so pork meat is a widely consumed, yeah, and value for high protein and nutrient contents. And the global pork production is projected to reach 131 million tons by 2028. As a previous professor just now told that people increasing, yeah, the volume of increasing million by million. So we need more POC to support these people. And beside that, the POC have a short shelf life, and especially under improper storage condition, and its susceptibility to spoilers and can lead to the economy losses and health risks to consumer. All right, so currently and traditional quality assessment methods are destructive and time consuming, and of course is unsuitable for the real-time application in the POC industry. And now we are focusing on the infrared thermal imaging. I think everyone's know the infrared thermal imaging. During COVID times, there's a lot of thermal camera in front of shopping mall and airport. Yeah? And it's a non-invasive method. And thermal imaging can indicate a microbial activities and generate image called thermogram. And when we combine it with machine learning, we can predict something from it. And of course, machine learning can enhance the classification accuracy of meat quality, and a lot of study, they're using the machine learning model like KNN, support vector machine, and QDA. So the objective of this study, we have two objectives. Actually, this is a type of a preliminary study. We are focusing on two conditions of storage to identify thermal imaging parameter of pod meat stored at 0 degrees Celsius and negative 15 degrees Celsius. And then to evaluate and compare the classification performance of for machine learning, we use QDA, support vector machine, SVM, K nearest neighborhood, KNN, and lastly is naive Bayes. For the methodology, we use 100 POC slices stored at 0 degrees Celsius and negative 15 degrees Celsius over 28 days. And then we use a thermal image capture using a FLIR TG165X. And of course, after that, the image will be processed. We do the feature extraction. We extract the ROI value, pixel, shape, and parameters. And after that, from that image, we classify it in, using a MATLAB. And then we are merge it with the model QDA, SVM, KNN, and naive Bayes. And after that, accuracy is evaluated with a confusion metric and cross-validation. So as you can see here, this is the infrared of, why it's not moving? Yeah, as you can see here, this is the thermogram, and then this is the raw image, this is a grayscale, and this is a region of interest, ROI. Right? So from the image, actually, this is only image results. We don't combine it with the physicochemical characteristic of the pork meat yet. We're still undergoing the study, and this is the first result that we found out. And then from the result and finding, we have average image parameter, correlation insights, and classification accuracy summary. All right. For the image parameter, we found that the major axis length peak at day 14 with the value is 4 to 6.33. And then the mean intensity remains stable, 0.56 to 0.58. And the maximum ROI consistent all across the day with the value 1.00. And this indicating that a structure changing and thermal footprints variation of the meat during the storage. Next is the correlation between all image between 0 degrees Celsius and negative 15 degrees Celsius. And then we found that a strong correlation was observed between the minimum and major axis length with R equal to 0.99 and at 0 degrees Celsius, and R equal to 0.9 at 6 at negative 15 degrees Celsius. And this indicating geometric consistent across storage conditions. However, there are low correlation for mean ROI, meaning that the suggests that temperature is inconsistent during the 28 days of storage. Now we go to the classification accuracy. First, we're talking about the SVM, support vector machines. We found that SVM has the highest validation accuracy with the value 83%, where it peaked at 84% on condition 0 degrees Celsius at day 14. Sorry. And 83% of classification accuracy for negative 15 degrees Celsius at day 0. And this trend showed the high and stable performance across most day. And SVM can generalize well for this task and handle the extract thermal feature efficiency. And it excelled in early and mid storage phase, but slightly dipped at day 21. As you can see that day 21 have the lowest classification accuracy, 57% and 65% for each storage condition. Next is a naive bias. For this one, we have a 78% of validation accuracy, which where 78% at 0 degrees Celsius at day 7, and 75% at negative 15 degrees Celsius at day 0 and day 21. And this trend show that more balanced but slightly lower performance across the board. And this machine learning can provide a consistent but moderate accuracy, likely limited by its assumption of future independence. Next is KNN. So the classification accuracy for the KNN showed that accuracy validation is 74% validation accuracy, where 85% at negative 15 degrees Celsius on day 7, and 85% at 0 degrees Celsius at day 21. And it's highly variable across the day and strong spike, but unstable. And this machine learning can capture a complex local variation, but was sensitive to sample distributions and noise. So it still have a noise in the image of thermal imaging when we capture the image, and then we validate with the KNN. Next is the classification accuracy using QDA. QDA is the lowest accuracy, where it's 72% validation accuracy, with 86% at 0 degrees Celsius with day 7, and 80% at negative 15 degrees Celsius at day 14. And this trend showed a strong performance at early to mid storage, but dropped at day 21. And this machine learning show robust accuracy during the initial freshness window, but lack consistency over longer storage. So what we can find here, SVM is the most reliable model in terms of validation accuracy and balanced performance across both temperature. However, QDA and KNN occasionally outperform SVM on specific days, and indicating they are strong alternative depending on dataset behavior. And then the third one, what we can find here is a naive bias with a solid baseline, but may underperform if future relationships are non-trivial. And lastly, the storage temperature effect, most models perform at negative 15 degrees Celsius for later storage day, likely due to the more stable thermal feature in super cool condition. So what we can conclude here, machine learning's model effective classify pork meat storage conditions, and I believe not only for the pork meat, but also for the fresh vegetable and fruits also, we can try it. And of course, they have study on it. And thermal feature also predictive correlation trends. SVM and QDA perform consistent well, and potential for non-invasive or non-destructive quality control in meat industry. I think that's all for me. I think, and I hope that can be interesting with you with the thermal imaging thing. Yeah. So this is our campus. Unimasku sayang meaning say, I love Unimas. Sayang mean love. Malay word.
So the presentation was only 10 minutes.
Yeah.
So we have enough time for discussion. Are there any questions? No? Okay, then Many thanks for your presentation.
Thank you very much.
Now we have a presentation about lichen symbiont microalgae potential for food and feed applications. So it's a presentation from Miriam Catala Rodriguez. Many thanks for your coming.
Very much.
And it's your floor.
Thank you. Oh, no, not this one. This one. Okay. Okay, I want to thank the organization for inviting me to this marvelous conference with so many interesting people from many fields. I'm a newcomer to this field, and I am going to talk about lichen symbiont microalgae potential as food and feed opportunities. Okay, well, you are all aware that global warming will increase the risk and intensity of droughts, not only in some countries, but all over the world, and very especially in Europe. The projected scenarios for the next years are not very nice, and especially in Southern Europe, in the Mediterranean area. Drought brings very, very hard consequences, both for agriculture and society. To crop loss, we must add food and feed price increase, unemployment, and inflation. A severe drought in 22 caused a very hard increase in prices of food in Spain, even to olive oil, which is the star of Mediterranean diet. And this just dragged the inflation of other products all over the country. And it was very hard for workers to pay for food and for farmers to pay for feed. So it is very hard. And now I must introduce you, because I guess that you don't remember what lichen is. It's not a fungus, or not just a fungus. It's not just a plant. It's not a weed. And well, is it edible? Well, let's see. Lichens are associations, symbiotic associations of very different organisms coming from different kingdoms. There's always the main component, which is fungus, okay, the microbiome, and there may be one or several photobionts that can either be green microalgae or cyanobacteria. Okay, we now know that there are other components, bacteria, yeast, but these are the main two, the fungus and the photobionts. They don't possess organs to absorb or maintain water inside the organism. Therefore, they continuously desiccate and rehydrate, which is a very strong stress on all the organisms involved in the symbiosis. As you may have heard, there's a positive result in this interaction of very different organisms. And at this point, I would like to just join to Professor Friedrich call for partnership and interaction between very different cultures and researchers from very different fields. In biology, symbiosis of organisms from different kingdoms, I'm not talking about different species, but different kingdoms, not only understand each other, but they generate a synergy, a positive synergy that allows them to inhabit extreme habitats. Okay, so lichens and lichen microalgae tolerate extreme temperatures, very high sun irradiances, hypersaline environments, even heavy metals. They inhabit mines with high levels of heavy metals. And all these properties are related with their adaptation to anhydrobiosis. That is to say, total desiccation. They tolerate total desiccation and they come back to life. Even the astronauts are interested in lichen microalgae. Could you start the video, please? And let's hope sustainable living on Earth. Oh, sorry. No. As you also may know, the industrial and biotechnological potential of free living aquatic algae is being developed. But we also know that some microalgae coming from lichens, isolated from lichens, are sources of bioactive compounds with remarkable biotechnological and even pharmaceutical potential. Some years ago, we demonstrated that this very well-known lichen microalga, Acerocloris erisi, could inhibit the cellular cycle. It was cytostatic, preventing tumor development in a fibrosarcoma cell line, mammal fibrosarcoma cell line. Well, lichen extremophile microalgae are natural sources and have high content of very infrequent bioactive molecules, such as polysaccharides, carotenoids, phenols, and unsaturated fatty acid, with antiviral, antibiotic, and antimicrobial activity, and could be a possible source for substitution of food additive with endocrine disruption potential. So I think that they possess a great interest for development. So the aim of our work is to analyze the content of some of these bioactive products in some genera of lichen microalgae, such as Cocomyxa, Sterocloris, and Trebuchia, and compare it with the aquatic microalga Chlorella vulgaris. Well, while they all possess more or less the same water content, according to their adaptation to dry environments, lichen microalgae desiccate very slow. They are able to retain a lot of water. But the antioxidant capacity and total phenolics are higher than in Chlorella vulgaris, also according to their ability to tolerate strong environmental stresses. Above all, in Cocomyxa solorina, this seems to be a very good source of both phenolics and other antioxidants. If we go to carotenoids, we see that the total content is similar in Trebuchia and Asterochloris and reduced in cocoa mixture. But surprisingly, the levels of lutein, which is one of the most interesting commercial products, is almost fourfold compared to chlorella. Regarding other pigments like the xanthophyll group, we see that they all possess quantifiable levels of all the xanthophylls except for astaxanthin, which is only present in Trebuchia. And we see that the contents in cocoa mixture of all of them is very notable. We also perform some dehydration studies using near-infrared spectroscopy, and we could observe that there are very interesting peaks of both saturated and unsaturated fatty acids, above all in this region. And one problem that has been mentioned by a colleague that has spoken before me, dehydration may bring microbial attacks or even loss of antioxidant or bioactivity bioactivity loss. But in these algae, which are adapted naturally to these desiccation cycles, this is not only a problem for these bioactive products, but in the case of unsaturated fatty acids, they increase if we refer to fresh algae and also saturated fatty acids. We have not looked over polysaccharides and polyols, but my colleague that is doing the research on this adaptation of Trebuchia algae to Mars culture or to space culture has found interesting results on that field on the polysaccharide and polyol content. So the conclusion is that these algae show an excellent bioactive compound profile, and their culture could be low cost, low water demanding, and could be an interesting option to develop for biotechnological and food industry. I would like to thank my colleagues from Rey Juan Carlos University, Isabel Sierra and Sonia Morante from the research group on analytical chemistry applied to the environment, food and pharmaceuticals, and also the symbiogenesis team from University of Valencia, and especially to Marta Pérez Rodrigo and the European Space Agency Discovery Project for the video on growing algae on Mars. And thank you all for your attention.
So many thanks for the presentation about future options. Are there any questions?
Thank you, Miran, for your presentation. I have one question about the purpose of evaluation of different microalgae when you compare with chlorella. Because chlorella now is available, is commercially available, and it has been regarded as a legal food ingredients worldwide. And have you only compared the basic nutrition and some phytochemicals? And have you, for example, have you distinguished some kind of, we thought the undesirable compounds in the three microalgae? Or
undesirable.
Yeah, undesirable. For example, some allergic or this kind of compounds.
As I have shown you, we are the only group that has tried to examine the bioactivity of this algae and the toxicity of these algae. In the fibrosarcoma murine cell line assays, we found no toxicity. When we put directly the killed autoclaved algae inside the cultures, and we observed no toxicity. Toxicity was 0. We only found this a little decrease in a little increase in free radicals in the culture. It was slight, but it was it could be observed, and this cytostatic effect on the cell cycle, which is identified with anti-tumor activity. But this is only one study.
Yeah.
I mean, this is this work is a little bit, well, it was we only published it on the 21st on the 2021. It was hard to publish, but I think that there is a great future for these algae, but they need to be investigated.
Okay, thank you.
Thank you.
Other questions? No? Thanks for the presentation.
Thank you very much.
So the next presentation is about inhibitory effects of chlorophyll pigments on the bioaccessibility of beta-carotene. But what are the benefits of chlorophyll? So the floor is for you.
Yeah. Okay, hello everyone. First of all, it's our pleasure to be here to present our study. And first of all, we would like to also thank you the invitation from Mate for our presentation here. And as Miran has introduced the macroalgae, and here we would like to say more specific about the photochemicals also present in macroalgae, and also in higher plants and in everywhere that is chlorophyll pigments. Here, I come from Southwest University, lies in southwest part of China, and specifically from College of Food Science. Okay, chlorophyll pigments, because in our lab, and since a long time that we have a long story for the investigation of chlorophyll pigments. For example, in higher plants, that only A series and B series of chlorophyll were found, but in algae, including microalgae or macroalgae, that there are more chlorophyll derivatives, and including the cyanobacteria, and there are more chlorophyll derivatives were found. That's natural chlorophyll pigments. And since a long time that we have this is the publication about chlorophylls in our lab since 10 years ago before. And here, including several chapters, and this is also involve many international cooperation. And today, I would like to only present our recent study about the intervention of chlorophyll pigments and beta-carotene, another photochemical, and carotenoids. And also, we will need to think how to reflect the beneficial or healthy promotive effect of chlorophyll pigments, and we will see some results. For example, because chlorophyll pigments and beta-carotene are both belonging to the liposoluble. We call it also the fat-soluble nutrients or micronutrients. So always they will share, chlorophyll pigments and carotenoids will share the similar pathways to be to enter our body. And meanwhile, because due to the liposoluble property of this kind of compounds, maybe the beneficial or healthy effect maybe in our destiny, because the majority of these kinds of compounds will not be absorbed in our body, and maybe they will in fact exert their influence, promote a healthy influence in our destiny, and it is more related with the intestinal flora or the gut microbiota. And in this way, this paper was published recently, is about the interaction between chlorophyll and beta-carotene, because that they share the same pathways to enter into our body, but other phytochemicals or other like polyphenols and other liposoluble macronutrients also show that promotes or inhibit effect. But for chlorophyll pigments, right now there is no such a study or investigation to see how it goes. And for this, that's due to the accumulation. The first obstacle to solve this problem is that we have to got enough and pure chlorophyll standard. But right now in the market, for the commercial chlorophyll standard, there is a limit, because in the agency or international market that we can only obtain, for example, chlorophyll A, chlorophyll B, phenolphthalein and phenolphthalein A. But for other chlorophyll derivatives, there is a huge limit for the availability. So in our lab, that currently we can produce and isolate and purify and obtain nearly 40 natural derivatives of chlorophyll pigments. So in this study, that we select the most common chlorophyll derivatives in our daily life, including chlorophyll A, B, chlorophyll light A, chlorophyll light B, and phenolphthalein A, phenolphthalein B, and phenolphthalein A and phenolphthalein B. And also we would like to screen the effect of the oil, edible oil, like the corn, coconut, medium chain fatty acid, and peanut, and olive, and fresh fish oil. And to see, this is the design of the experiments, because for the chlorophyll pigments that we select for phytylated chlorophyll, and meanwhile also for dephytylated chlorophyll. And in this way, this can have a full understanding, more or less, about the chlorophyll pigments and its influence on the beta-carotene bioaccessibility. And finally, because the basic scheme or approach to investigate is use an in vitro digestion, because in vitro digestion is very fast and easy to carry, and regardless of the animal welfare, this kind of thing. And also, finally, the result will be validated by animal side. Because also due to the in vitro digestion, we use several indicators to show the influence of chlorophyll pigments on the beta-carotene bioaccessibility. And according to the study that we found, first of all, dephytylated chlorophyll, for example, phenolphthalein A, phenolphthalein B, and chlorophyll light A and chlorophyll light B, they inhibit the beta-carotene bioaccessibility severely, and very obviously, like here. Like here. And also, if we study, because this is a mutual influence, if we study the bioaccessibility of the added chlorophyll pigments, we can also see difference. That's, for example, for phytylated chlorophyll, the bioaccessibility rates, there are a big difference if you if you take into consideration of beta-carotene. But for the defethylated chlorophyll, the influence is not so obvious or not so significantly compared with the phytylated chlorophyll. And even because before we also use chlorophyll pigments for the in vitro digestion independently. So in this case, if we add beta-carotene, and there will be some kind of severe difference between compared to before, that's even after in vitro digestion, I mean in the acidic gastric conditions, that we will also find the green chlorophyll, which means the magnesium atom in the middle of the fetal chain macrocycle remains still. And also for phytylated chlorophyll, that's before, if we use magnesium-free chlorophyll pigments like ferritin A, that we will find important reactions, that is phosphorylation reactions. But if we add beta-carotene, that no phosphorylation reactions were observed, which means that, for example, the beta-carotene and other phytochemicals, if it were added, it will exert some kind of protective influence for chlorophyll pigments. And in return, of course, the beta-carotene bioaccessibility itself will be depressed. And also, we will determine the optimum volume for oil and also the chlorophyll concentrations on beta-carotene bioaccessibility, because in our natural, I mean, in our daily ingestion of these kinds of fruits and vegetables, that's the ratio. Of course, chlorophyll pigments is much more than carotenoids. So in this case, that you can see from, okay, you can see from this symbol that if we add chlorophylls, of course, the beta-carotene bioaccessibility will be depressed along with the chlorophyll concentration. And meanwhile, we analyze the particle size and the data potential of the macrofluids, including the digester and the micelles. What is interesting is that, for example, for defethylated chlorophylls, there are big differences with the phytylated one, which means without the fetal chain of this structure, that chlorophyll pigments can form smaller micelles compared with phytylated one. And for the olive oil is regarded as from this data, olive oil regards the best for the chlorophyll or beta-carotene, this kind of bioaccessibility. Also, for the data potential, this kind of analysis, that my micelles with defethylated one is more stable, much more stable than others. Finally, with the mice assigned to validate our results, you can see directly that this is the beta-carotene alone. And if we add the chlorophyll alongside the ingestion of beta-carotene and use mice aside, that all the accumulation related with beta-carotene and the retinal accumulation were depressed, which means that the chlorophyll pigments, if you want to, make sure the supplementation of beta-carotene, that chlorophyll pigments is not an ideal component or additive to add in the beta-carotene supplements. And so as far as now that we know that chlorophyll pigments, especially the defethylated one, I mean the smaller molecules, decreased the bioaccessibility of beta-carotene by impeding methylation and promoting the degradation of beta-carotene during in vitro digestion. And we need to think about what's the benefits of chlorophyll pigments, because according to observations or epidemic say that human, I mean, which consume more fruit and vegetables, has less risk for vascular diseases or non-chronic diseases. So it has some kinds of meaning that the phytochemicals inside fruits and vegetables will exert some kind of beneficial effect. So the next step is that we should see the interaction between chlorophyll pigments and the intestinal flora. And that is from our observations. And this publication is the recent one, but only in Chinese journals. And and some investigation is also undergoing, and we will publish more. For example, because we've got also the current understanding about chlorophyll pigments is only limits on the chlorophyll extract, which means that, for example, you use spinach leaves and you extract chlorophyll, but meanwhile, you will also extract other phytochemicals like polyphenols and also carotenoids. And in our assay, we would like to use pure chlorophyll pigments and to understand exactly how chlorophyll molecule interact with the intestinal flora. And in this case, that's we use the high-fat diet, high-fat mouse, because it seems to be that the phyophytins modulates the gut microbiota in the HFD diet via the Fricka fermentation. Initially, we also use the in vitro fermentation, this kind of protocol, to understand primarily at the beginning whether this is feasible and how it will go. Of course, we also admit that's the difference between the in vitro ones and the in vivo ones. And finally, we will right now we are also using the in vivo ones for further study, and which is undergoing. And we will feed the mice with a high-fat diet, and then collect the feces, and then use phyophytins to fermentation. And finally, we will identify the change of the gut microbiota and also the short fatty acid and the analysis of microbiota metabolites. And in this case, that's according to our study that both phyophytin A, firstly with the magnesium-free chlorophylls, both phyophytin A and phyophyllite A increased the abundance of the Brodobacteria and decreased the abundance of some kind of pathogenic bacteria. And also that we found the metabolites of the intestinal flora with phyophytins will produce some kinds of antibiotics like compounds. Even this is much bigger or much more significant for the phyophyllite A, which means without the phytol, it seems that the interaction between intestinal flora and the chlorophyll pigments is even more significant, or it is more intense. And also the short fatty acid. Some short fatty acid will be stimulated or will be promoted by the addition of chlorophyll pigments. And this is about the phyophytins. And what about the magnesium-containing chlorophylls? Because normally, that we saw that the chlorophyll pigments that we get from the higher plants is chlorophyll A and chlorophyll B. But after digestion, that the chlorophyll pigments will disappear or will be transformed into phyophytins in the intestinal. But if you protect the chlorophyll, for example, if the chlorophyll was in macros capsules or in some mixed with other food ingredients, the chlorophyll A and chlorophyll B will turn up in our intestinal. And so in this case, especially chlorophyll A and chlorophyll B exerts the, potent antioxidant properties compared with phyophytins. In this case, we also use chlorophyll A and chlorophyll B for the in vitro fermentation. And we also found both chlorophyll A and chlorophyll B increased abundance of the firmicutes and decreased also the abundance of some pathogen bacteria. And also the metabolite indicates that the addition of chlorophyll pigments will stimulate some kind of antibiotic-like compounds in the fermentation. But the in vitro fermentation shows that no big difference between after the addition of chlorophyll pigments about the short fatty acid produced. So it means the same, but in our in vivo assay, it did. So in this case, that we also found the chlorophyll pigments will have some kind of influence about the high fat diet, fat mice feces, and the interaction between them should be for in-depth investigation. And in this term that we use the in vivo analysis, means the mice. Also, in this study, we use the in vivo animal experiment to further explore. And based on previously investigation, that we only select 4 types of chlorophyll pigments. That is chlorophyll A, chlorophyll B, furfurin A, and furfurin A. Also with the HFD mice models. And in this case, because in our daily diet, in higher plants, only chlorophyll A and chlorophyll B, and chlorophyll B only occupy maybe 1/4 of the total chlorophyll profile. And in other cases, for example, in many macroalgae, that the furfurin A occupied a lot. And also in our previous study, according to the proof that the furfurin A exerts more influential consequences on the intestinal flora. And this including the animal liver, intestine, and fat sections about the high HFD masses after the ingestion of chlorophyll pigments, and also the changes of gut microbiota and the short fatty acid and other metabolites. In this case, except for chlorophyll B group, until now, I don't know why chlorophyll B is so special. And other chlorophyll-treated groups significantly improved the hepatic lipid accumulation and other lipid metabolisms in the liver. And also for the intestinal health, and also the addition of other chlorophyll pigments improve the side effect induced by the high HFD diet. And also the furfurin A and I will accelerate. Furfurin A effectively ameliorates the enlargement of some fat tissues and the dispersion of many, for example, the bad cells. At least if we investigate the intestinal flora, we can find that the especially for furfurin A, the fatal-free chlorophyll pigments can restore the relative abundance of lactobacillus. This is furfurin A, but this is the control. The lactobacillus was extremely decreased after the ingestion of a high-fat diet. But if we supplement it directly, meanwhile with furfurin A, it seems that the lactobacillus will be recovered. This is a good, important findings of our study. And also the short fatty acid. Generally speaking, that the short fatty acid will be stimulated or will be increased, and the total amount is increased. And in this thing that we found that the furfurin significantly improved the lipid metabolism, and with the great finding that the lactobacillus is our key intestinal bacteria that we need to investigate more about the interactions between fulvophyte and the lactobacillus. And we also isolate the specific strains of lactobacillus from this kind of mode. And also the undergoing analysis is because we need to find the specific signal pathways and the medications, including the qPCR and the West blotting, and also the target metabolomics to to decipher the intensive mechanisms beyond this kind of phenomenon expressions. So that's almost all. And these recent studies were all sponsored by our national key R&D program of China, and thank you. And thanks again for your attention, and also thanks a lot for the invitation. Thank you very much.
So because of the time, we have no time for questions. You can ask during the lunch break. So we will have now the next presentation from Akos Bata about development and consumer acceptance of functional instant coffee enriched with dietary supplements.
Good morning or good afternoon already. I welcome you all in Budapest. My name is Ákos Barta. I'm from the Hungarian University of Agriculture and Life Science. I'm a PhD student currently. And let's say I'm also an entrepreneur. And within my presentation, I would like to present you a real development and also a sensory test related of a product which is also already, let's say, on the market. The aim of our research was not only to develop a product, but also, let's say, we try to focus on many other things as well. Oh, sorry. Yes. Thank you. So we also wanted to focus on some nutritional aspects as well, like the low fiber intake of the Hungarian population, for example. And from the agricultural point of view, during the development of this product, we also, let's say, wanted to use secondary agricultural products as well, like, for example, in this case, bovine collagen, which is, you might know, not only a source of protein, but also, let's say, a secondary agricultural products. As you can see here, let's say we started with some bibliometric analysis. For example, what kind of ingredients what we use exactly? Like, for example, what type of organic magnesium salt has the best taste or homogeneity, which was for us very important. And we tested a lot of mushrooms. We tested a lot of prebiotic fibers as well during our research and development, let's say, to find the final formula. In case of instant coffee, we used a freeze-dried 100% Arabica instant coffee. The thing with instant coffee, let's say in Hungary, is that the quality of instant coffee, let's say, considered generally low. So it was also a challenge for us to see how different type of products with instant coffee or fortified instant coffee, let's say, will be good or not for the consumers. As I said, this product is already, let's say, on the market. So we also have other type of insights from the end consumers. And that was very interesting for us because, let's say, for the research group, that the Hungarian consumers prefer bovine collagen, for example, prefer or see the quality of the bovine collagen is higher than, for example, porcine collagen or fish collagen in this type. So that was the reason why we currently only use bovine collagen in this product. We also have to do some preparations with our raw materials as well. So, for example, we have to grind the freeze-dried instant coffee, because normally the freeze-dried instant coffee looks like in big or comes in bigger granules, and those type of bigger granules we cannot use in the other powdered ingredients. And of course, after that, we mixed all the ingredients like the freeze-dried coffee, the prebiotic fibers, the mushrooms, the magnesium, and the bovine collagen together to create, let's say, the current end product. Here you can see the current end product. And this is the product what we used and also will be using in the sensoratory or during the sensoratory tests as well. As I said, for us, it was important to use dietary fibers as a type of prebiotics in the end products, also agriculture byproducts, like in this case, the bovine collagen peptide. So it's hydrolyzed collagen, and the other nutritious or nutraceuticals, let's say, in the end products. But in this case, the most important was magnesium for us. We started the sensory test. The sensory test had two, let's say, samples. One was, let's say, a normal instant coffee, but it was the same freeze-dried instant coffee what we are using in the fortified product as well. And the other was the freeze-dried instant coffee enriched with the nutrients, as you could see on the last slide. We started to evaluate our results with the first 155 respondents. This was a blind test, and I can show some results of this sensory test and our research. Interestingly, women were more interested in our sensory tests. And of course, people who are already drinking coffee, at least one or more a day, was more interested to taste the instant coffee and our fortified product. The first result, which was very important for us, at least, that the homogeneity was very good. So there was, let's say, no difference between the homogeneity of the normal instant coffee and the fortified one. This was very important for us because, as you might know, normally magnesium salts can taste very, very bad, and the solubility could be also very bad, similarly with the case of prebiotic fibers and mushrooms as well. When we started to also analyze the differences between appearance, aroma, and taste, there were differences between our consumers. Just to show you a few results in this case. For all the respondents, let's say, the taste was superior, even in the case of instant coffee and in the case of fortified instant coffee. We also realized that people who like to tend to drink more, at least 2, 3, or 4 coffee a day, at least in Hungary, they still prefer the strong, robust taste. And if the taste is lighter, like let's say more fruity, they gave us worse response in this case. Aroma and appearance was not so important, at least in our results. And for us, there was two very interesting things related to the fortified, so the product enriched with the nutrients, is that people who add some sweeteners, sugar or honey or some artificial sweeteners, or milk or milk alternatives like rice drink, for example, that was also possible. They gave us more positive results on the product's quality, taste, aroma, and all the appearance. And in this case, the performance was higher when the respondents added some, as I said, sweetener or milk products to the fortified instant coffee. We also think now, analyzing the data, that somehow, especially dairy products or the milk alternatives may have a positive effect on the product's quality and taste as well. Generally, and as a summary, the majority of the respondents had a positive perception of the fortified instant coffee as well. As you could see, the taste was very, very important, especially if someone, let's say, used to drink more stronger or robust type of coffees. But we still see the potential for developing similar products as well. We already started to do the same research and development with dark chocolate, so fortifying dark chocolate with magnesium, zinc, etc., etc. In the same way, we also started a study with matcha tea, not only of the chlorophyll content, for example, but the other things as well, like fortifying matcha tea with certain type of ingredients, prebiotics, collagen, etc., etc. And we also started the research with instant kombucha powder as well, like making also the pre and the probiotic effects somehow together. So not only using dietary fibers, but also, let's say, start to use probiotic strains as well to develop certain type of products for more nutritional benefits and for more nutritional value. Thank you for your attention. I hope we still have time for questions as well.
We have enough time.
Okay.
So are there any questions? You don't like coffee? Okay, so many thanks.
Thank you.
We will have a last presentation before the lunch break from Sinabu Hailu Zium. It's about non-destructive evaluation of Bruce Bloom quality changes during storage using lean-based laser light backscattering imaging.
What is your presentation? No, I don't know. Do you have it? No, today's no. Okay, then how we can get it? I was thinking it's already with the email. Okay. Okay, sorry for my technical error. And good afternoon, and my name is Dr. Hailu. And first of all, I would like to thank you for the organizers for giving me this opportunity to present our work. So the topic is on non-destructive evaluation of Bruce plant quality change during storage using line-based laser light backscattering imaging technique. As an introduction, as we know, the plum fruit is one of the most valuable fruit, stone fruit, and it's known due to its the commercial significance, nutritional value, and health benefit. However, this fruit, its quality is damaged because of the post-harvest handling and storage. One of the most common problem in this process is the mechanical damage. So this mechanical damage induced an bruising effect. So this bruising effect changes the physiological and the metabolical process, and this process speeds up the ripening and softening of the fruit. So traditionally, the visual inspection method is used, but it has a limited accuracy. And the other one is the destructive method. These methods are, even though reliable in the measurement, and they are internationally acceptable, but they have a limitation with producing high wastage from the product, from the sample product, as well as they consume high energy, the cost also for operating cost is very high. That's why, thank you nowadays for the advancement of the technology. There are an increased demand for looking the fast, cost-effective and non-destructive technique. Therefore, the line-based laser backscattering imaging technique is one of the non-destructive technique, which operates based on the principle of light backscattering or diffuser reflectance and the image processing in the wavelength region of the visible and NIR. So the aim of this work was just to monitor the quality change of the Bruce plum during storage. So with this, the system utilized a single laser module, which the laser light is emitted from 635 nanometer. And then the signal, the signal approximation approach was used to extract the features, and these essential features used to establish a model which predicts the firmness and the solid content of the plum. So the material and mass, the plum, the top and plum were collected from the commercial orchard, which is located in Korosh. This place is, I think, 125 kilometers far from Budapest to the southern side, as shown in the image. So the plum are shown in the picture. To about 220 plum samples were collected, and from this, all of the plum is mechanically induced to with from 1 meter height to induce the bruising, and then after that, the 30 of the samples were used for initial measurement, and the remaining 180 was used for the treatment, which is stored at 1, 10, and 22 degrees Celsius for up to 21 days. So at first, the non-destructive measurement is carried out, and then followed by the firmness and solid content using a destructive technique, which is for firmness hand penetrometer, and for the solid content refractometer. So this measurement is held every 7 days interval. From each group, we use 20 samples. So as shown here in the picture, the system is already looks like this has two major parts. The first one is the system. This one has a dark chamber, camera, and laser module, and this is the sample. So the laser module illuminated the surface, and from this surface, the camera captured an image non-destructively. So this image is processed with a self-developed algorithm using a Scilab. So from this, the RGB image is converted or transferred to a gray image. And from this, the peak profile is extracted only from the 5 pixel around the center, from the center of the peak. So after we after extract this intensity profile, we apply the empirical mathematical model, which is a Cauchy distribution function, to fit the curve. And from this fitting curve, we extract 3 important parameters, which is the H. H is the amplitude value or the height of the peak. And the S is the shape, which is the peak narrowness and wideness. And the other one, the third parameter, is full width at half maximum, which is calculated with, compete with the 2 times the shape value. And when we see the data analysis, we use 2 softwares. One is the R software in order to analyze the basic distributive statistics, ANOVA, and correlation, as well as the model. Here we use 3 types of models. It's not displayed. Yes. Sorry. So here we use prediction, 3 different prediction models, which is one is the multivariate regression model, and the other is support vector motion, and the third one is multivariate adaptive regression spine. So for these models, we use an image extracted data with 3 variables and 420 observations. This model is, their performance is cross-validated with bootstrapping, followed by Monte Carlo technique. So as a result, when we see the basic statistics, the firmness of the fruit is decreased across all temperature, especially on the first 7 days. However, the highest acceleration rate is observed those fruits which are stored at 22 degrees centigrade, which is at a higher. This may be possible due to the damage of the tissue and the loss of the moisture or the hydration and the oxidative stress. The solid content also showed that there is an increment across all the temperature and time group, but still the higher conversion of the solid is observed on the last storage temperature group at high. But when we see on the last day stage, the precision or the deviation of the standard deviation of each day is very higher compared to this. This may be related with the structural damage of the fruit, which makes this highest deviation across the group. This is the real experimental result with the plan photo. This is the before the treatment, and this is after the treatment. It's like, but with extended storage time, some on those fruits which stored at low temperature gives a sign of some defects, which is related with the chilling injury. And the other is the person's correlation. This showed that the linear relationship between the variables. When we see the LLBI parameters, the amplitude, the shape, and fluid at half maximum is strongly correlated with the firmness and solute content of the plant. However, if we see the shape value of the profile, it is positively correlated with firmness and inversely with a strong correlated with solute content. This means at the solute content becomes higher, the scattering ability of the photon on the tissue becomes unlimited or cannot further go, and the absorption is higher than on rather than in the scattering. So this may be the signal influence due to the textural change as well as the internal composition. So the models performance, when we see the models performance for the two parameters, when compared, the Mars is better, relatively better performed than the two models. So with visual, we can see in the visual way. This the Monte Carlo simulation also showed that the precision for the R squared, the coefficient of determination, and the root mean square error shown after the 50 iteration. I think the variation is more small and they become stable. So the efficiency of this model is better for the prediction of the firmness as well as for the solute content. However, when we see on this plot, there is a variation, temperature-driven variation at lower measured value on the firmness and at higher value of the solute content. So this is this attributes to the change on the tissue optical properties. So this tissue optical, the change tissue optical property leads to the limit the scattering ability of the fruit, the photon. At the conclusion, we see the storage temperature and time it significantly affects to the fruit firmness and solute content, and the LLBI-driven optical parameters can have a strong correlation with this parameter, and then this Mars model is the best for prediction of this parameter. Then these results give a final conclusion of this line-based LLBI has a promising result for assessing the bruise plant during storage as a non-destructive way. These are some of the citations, and thank you for doctoral food science and the Stipendium Hungary Scholarship. Thank you so much.
So again, many thanks for the presentation. Are there any questions? We have 10 minutes time. No questions? Then enjoy the lunch.